Hello and welcome to our next lecture. Today we're continuing the discussion of how to solve the Laplace equation. We solved one special case where only one part of the boundary was non-zero. Today we're going to consider three other special cases when other pieces of the boundary become non-zero. So the next special case that I want to consider today is the case where the lower boundary is non-zero. So in that rectangle we have Laplacian u being 0. We maintain zero boundary conditions here. But we also maintain zero boundary on the top. But a non-zero boundary on the bottom. In 3 dimensions, this is. We have zero boundary all the way through except at the x-axis. And the surface probably will look something like that. We use the method of separation of variables and we're going to use it again here. We assume that u of xy equals the summation of Cn u sub n of xy. Each u sub n satisfies the differential equation, and each u sub n of xy is a product of two functions. Also, we assume that each function u sub n satisfies the zero boundary conditions where the boundary is supposed to be 0. So u sub n of 0y should be 0, u sub n of ay should be 0, u sub n of x 0, well, we don't know, and u sub n of xb is going to be 0. Plugging all of those in the differential equation will lead to, yet again, that x double prime over x should be equal minus y double prime over y, and that should be equal to the constant negative sigma. We do have boundary conditions on x and y derived from the boundary conditions on u sub n. We have that x of 0 should be 0, x of a should be 0, and now we have another boundary condition that y of b should be 0, instead of y of 0 being 0. Just as before, when we derive solutions to the x of x and y of y, since x has two boundary conditions imposed on it, we're going to solve it first. We derived that the constant sigma should be n pi over a squared, and the solutions x of s should be just sine of n pi x over a. For y, we have the following equation, that y double prime minus n pi over a squared times y should be 0. And we also know that y of b should be 0. Just as before, this leads to two solutions for y. That's alpha 1 times e to the minus pi n over a y plus alpha 2 times e to the positive pi n over a times y. Imposing the initial condition that 0 must be y of b, we get that alpha 1 times e to the minus pi n b over a plus alpha 2 times e to the positive pi n b over a should be 0. This is slightly more complicated than the previous case. Solving for alpha 1 we get that it should be minus alpha 2 times e to the 2 pi n b over a, and therefore y of y has the following form. It's going to be minus alpha 2 times e to the 2 pi b n over a times e to the minus pi n y over a plus alpha 2 times e to the positive pi n y over a. I would like to assign a value to alpha 2 so that these functions will look more or less uniform. So if I assign the value to alpha 2 to be e to the minus pi n b over a, then this will become e to the pi n times y minus b over a minus e to the minus pi n y minus b over a. There is no specific reason to assign this value to alpha 2, except that when I assign this particular value to alpha 2, I get functions that are a little bit more symmetric, and it becomes immediately apparent that when I plug in y equals b, both exponentials evaluate to e to the 0, and then we get 1 minus 1, and that's 0, and that this function satisfies the boundary condition that I prescribed. Therefore, u of x, y is going to be the sum as n goes from 1 to infinity. As I said before, n will have to go from 1 to infinity because that is dictated by the solution for the function x of x. Cn times y of y, which is e to the pi n y minus b over a minus e to the minus pi n y minus b over a multiplied by sine of pi n x over a. So now the question is, how do you determine the coefficient Cn? Well, we do know that u of x0 equals g1 of x, and that should be the summation of Cn. And now I plug in y equals 0, so it's e to the minus pi n b over a minus e to the positive pi n b over a times sine of pi n x over a. And therefore, the coefficients Cn are determined as the coefficients for the sine expansion of the function g1 of x, except that every coefficient, since it has an extra multiplier in front of it, we have to bring it in front of the integral. So it's going to be 2 over length of the interval, which is 2 over a, times 1 over e to the minus pi n b over a minus e to the positive pi n b over a, the integral from 0 to a of g1 of x times sine of pi n x over a dx. Once we find the coefficient Cn, we plug them into the sum, add up the functions, and we get the full solution. Alright, so this was another one of the special cases when I have other three boundaries to be 0, and then the lower boundary is non-zero. It's quite easy to see that when we switch to the other two boundaries, the left and the right boundary, the roles of the x and y will change, and we get the same formulas except that x and y will be interchanged. So let's list all of those four cases. Case 1 is when I have the boundary for y equals b non-zero. So this is the case where u of x b equals g2 of x, and that's non-zero. All the other boundaries are 0. In this case, u of xy was the summation, as n goes from 1 to infinity, of coefficients Cn e to the power pi n y over a minus e to the power minus pi n y over a times sine of pi n x over a, where each coefficient Cn was found as an integral 2 over a times 1 over e to the pi n b over a minus e to the minus pi n b over a integral from 0 to a of the function g2 of x times sine of pi n x over a dx. Case 2, the one that we discussed just now, is when the boundary at y equals 0 is non-zero. So in this case, u of x 0 is equal g1 of x, and that's not 0. The rest of the boundaries are 0. So in this case, u of xy, as we just derived, equals sum as n goes 1 to infinity, coefficient Cn, e to the pi n y minus b over a minus e to the minus pi n y minus b over a times sine of pi n x over a, where each coefficient Cn is found as an integral 2 over a times 1 over, this time we get e to the minus pi n b over a minus e to the positive pi n b over a, the integral from 0 to a of g1 of x times sine of pi n x over a dx. The other two cases are obviously talking about boundary conditions when x equals 0 and x equals a non-zero. So case 3. Let's first consider the case when we have non-zero boundary at x equals a. So this is where u of a y equals f2 of y, and that's a non-zero function. Easy to see that the roles of x and y are interchanged, and so the solution will be the sum that has exactly the same form as the sum we have up here, except that we switch the roles of x and y. So u of x y will be equal a sum as n goes from 1 to infinity Cn. Here we're going to have e to the pi n x over b minus e to the minus pi n x over b times sine of pi n y over b, where each coefficient Cn is computed as 2 over b times 1 over the exponential function e to the positive pi n a over b minus e to the minus pi n a over b, the integral from 0 to b of the function f2 of y times sine of pi n y over b dy. And then the last case, when we have a non-zero boundary at x equals 0. So in this case we have that u at x equals 0, y equals g1 of y, and that's a non-zero function. U of x y will be the summation just as before. Going to have exponential functions. And each coefficient is computed very similarly as an integration. This time I made a slight typo. This is a function f1 of y times sine of pi n y over b dy. In different texts and different books, the signs may be interchanged. The quantity, the difference of the two exponentials may have a name, sine hyperbolic, that's written as sine h. So if you see sine h, don't be surprised. It's not a different function. It's the same function. It's the difference of these two exponentials. It's just was given. I like to weigh the necessary functions, so that's why I'm sticking with the exponentials. But if you find the use of sine h and cosine h more convenient, you're more than welcome to use them. So this gives us 4 different cases where we have 4 boundaries non-zero. And if we have more than one boundary non-zero, we can easily see that we can just break the problem into 1 or 2 or 3 subproblems where only one of the boundaries is non-zero, and then add up the solutions, because each one of those functions, when you add them up, only affects one boundary and doesn't affect the other boundaries. So for example, if I add up the solutions for the case 3 and 4, you can see that I will preserve the upper and lower boundary being 0, and the left and right boundary will be exactly what they're prescribed for these 2 cases separately. So when I add them together, they will give me a solution to the problem where 2 of the boundaries are non-zero. There's one problem though. Each one of those functions, each one of those boundaries is required to converge to 0 at the corners. So if I add 4 of these functions, I will still have the corners at 0 value. But we know that this is unrealistic, and sometimes the corners may be at non-zero values. So what if I have 4 functions prescribed? So here I have a function f1, here I have a function f2, here I have a function g2, and here a function g1. And those functions don't converge to 0 at the corners. So for example, at the 0, 0 corner, when the function should be equal to g1 of 0 or f1 of 0, and that's what I'm going to call u naught naught, and that's not 0. And at the corner a, when I have g1 of a should be the same as f2 of 0, and that's something that I'm going to call u1 0, and that might be non-zero, or u of 0b, which is g2 of 0, which should be equal to f1 of b, and that is something that I'm going to denote u01, and that might be non-zero. And the uab, which equals g2 of a, and should be the same as f2 of b, and that should be something that might be non-zero. So what if I have boundary conditions prescribed so that the corners are not 0? Then these 4 subcases are not going to help us. Well, the solution here is to reduce the problem to the problem with 0 corners. That means I have to subtract something from the function u, or write it as an addition of 2 functions, so that one of the functions have all of the corners to be at 0, and in another function has corners to be non-zero, yet it doesn't break the fact that this summation of those 2 functions solves the differential equation. So I'm going to write u as a summation of w of xy plus v of xy, where the functions are constructed as the following. V of xy is a bilinear function, which I'm going to denote as alpha naught plus alpha 1x plus alpha 2y plus alpha 3xy. And I want my function v satisfy the values at the corners. It is very easy to see that the Laplacian of v equals 0. Because if I take partial derivative with x twice, I'm going to get 0. If I take partial derivative with respect to y twice, I again will get 0. So what are the values of alpha 1, alpha 2, alpha 3, and alpha naught? Well, v of 0, 0 must be exactly u 0, 0, and that's alpha naught. So alpha naught is an easy coefficient to find. V of a0 should be something that I denote u1, 0, and that should be, according to this equation, x equals a, so it's alpha naught plus alpha 1a. Therefore, alpha 1 can be found as u1, 0 minus alpha naught over a. Or, since alpha naught is u 0, 0, I can write it as u1, 0 minus u 0, 0 over a. So now that v of 0b, which is something that I denoted u 0, 1, that is, well, now x is 0, y is non-zero, so it's alpha naught plus alpha 2b. Therefore, alpha 2 equals a fraction of u 0, 1 minus alpha naught over b. So it is u 0, 1 minus u 0, 0 over b. The last one is that v of ab, which equals to u1, 1, that should be alpha naught plus alpha 1a plus alpha 2b plus alpha 3 times a times b. Solving this gives us that alpha 3 should be u1, 1 minus alpha naught minus alpha 1a minus alpha 2b divided by ab. Plug in the previous values. Alpha naught is u 0, 0. Alpha 1 times a is exactly u1, 0 minus u 0, 0. And alpha 2 is u 0, 1 minus u 0, 0. Everything divided by ab. Simplifying, I get u1, 1 minus u1, 0 minus u 0, 1 plus u 0, 0 divided by ab. So once I find these coefficients alpha 1, alpha 2, alpha 3, and alpha naught, then I will be able to formulate the problem for w. We get that w of xy is simply u of xy minus v of xy. The Laplacian of w of xy will be equal to the Laplacian of u minus the Laplacian of v. But since both of those Laplacians are 0, Laplacian of u is 0 because u has to satisfy the differential equation, and Laplacian of v equals 0 by the construction of v. So we get that the w itself satisfies the differential equation. Now, since w is not exactly equal to u, it cannot satisfy the same boundary conditions. So w has to satisfy different w conditions. So w of 0y, w of ay, w of x comma 0, and w of x comma b are all should be different. But since we have the boundary conditions for u, and since w is u minus v, then we can compute the boundary conditions as the boundary condition for u minus the value at the boundary of v. So this is equal to u of 0y minus v of 0y. And the same goes for all other boundary conditions. By plugging in the conditions, we get a new boundary value problem for w. We have that w xx plus wyy should be 0. At the boundary x equals 0, u equals f1 of y minus alpha naught plus alpha 2y. W of ay will be f2 of y minus alpha naught plus alpha 1a plus alpha 2y plus alpha 3 a times y. W of x0 will be g1 of x minus alpha naught plus alpha 1x. And W at x b will be g2 of x minus alpha naught plus alpha 1x plus alpha 2b plus alpha 3 times b times x. To solve this boundary value problem, we break it into 4 subproblems. So write W of xy as W1 of xy plus W2 of xy plus W3 of xy So W will have 4 components. Each one will satisfy the equation with only one boundary, non-zero. Say make W1 to satisfy the equation with F1, W2 satisfy the equation with F2, W3 will satisfy the equation with G1, and W4 will be responsible for making G2 boundary non-zero. When you add all 4 of them together and then add the function v, this will give you the final solution to the boundary value problem. So here I have a simple example. When I have x going from 0 to 4, y is going from 0 to 2, I have ux0. When y equals 0, I have a 0 boundary. When x equals 4, I have a 0 boundary. When x equals 0, I have a parabolic boundary that looks like that. It's a parabola that goes to value 1. And then when y equals 2, I have a piecewise linear function. Up to 2, this function goes down as a linear function, and then after 2 continues as a 0 function. This is how a solution will probably look like. Think about a piece of plastic stretched into this configuration, and then you'll get a good idea of how the solution looks like. So now I have to compute the function v, then I will have to, since I have only 2 non-zero boundaries, I will have to break the function w into 2 components. One component will be responsible for the boundary on the y-axis, and another component will be responsible for the boundary for y equals 2. And then I add all these things and I'll get the full solution. So in this case I get u00 at the corner is 0. u10 at x equals 4 is also 0. u01 is 1. Because if you plug in y equals 2 into the function u0y, you get 1. Or if you plug in x equal 0 into this boundary condition, you'll get that the boundary condition is at 1. And then u11 is again 0. So the coefficient for the function v can be computed as follows. Alpha naught is u00, and that's just 0. Alpha 1 was equal to u10 minus u00 over a, and that was 0. Alpha 2 is u01 minus u00 over b. u01 is 1, so it's 1 over 2. And alpha 3 was u11 minus u01 minus u10 plus u00 over a times b. I know that only one of those coefficients is 1, it's u0, 1, so it's just minus 1 over 8. And therefore my function v has the form 1/2 y minus 1 over 8 x times y. I will only have two non-zero boundary conditions for the function w. I will have that w at x equals 0 will be the function that I have, y times y minus 3/2, and I will have to subtract my v at 0y, so it's just minus 1/2 y. W at the end, x equals 4, should be 0, minus v at 4y, but at 4y, my v is always 0. W at x 0 is a 0 boundary, minus v at x 0, but if y is 0, my v is always 0, so it's just going to be 0, and w at x 2 was the step function, which I'm just going to call it g2, minus v when y is 2, so it's 1 minus x over 4. Then I will solve two boundary value problems, one boundary value problem that will talk only about this boundary, and then the second boundary value problem will talk about this boundary. And traditionally, I'd like to do these calculations with Mathematica. So here is my setup. I have a equals 4 and b equals 2. I've defined my functions f1, f2, g1, and g2. I defined my function g2 as 1 minus x over 2, only applicable on the interval from 0 to 2. I use the unit step functions to define piecewise functions. You can go ahead and use the piecewise command to define this function. That will not make any difference to the overall result. And let's plot the functions f1 and g2. So these are the boundary conditions. As you can see, they both agree at the corner. Both of them converge to 1 at the corner. And now I have to define the function v of xy as y over 2 minus x times y over 8. So this is the function. It is 0 at the two boundaries that are 0, but it's non-zero at the two boundaries that have non-zero values. And as you can see, if I subtract my function v from the boundary conditions, it will bring this corner to 0, but it will not touch the other corners. So here I provide a quick outline how we're going to break the boundary value problem into two subproblems. I have a boundary value problem with two non-zero boundaries, and I broken into two subproblems where only one of the boundaries is non-zero. So w1 will be responsible for the boundary at x equals 0, and w2 will be responsible for the boundary at y equals b. So here I implemented my formulas. I compute the coefficients. I add up the functions. For the second boundary value problem, I also compute the coefficients, add up the sums, and define two functions, w1 and w2, which satisfy just single boundary conditions. So here's how the first function looks like. Notice that it's kept its boundary values at 0. So now this is a shifted parabola. So it's not the same parabola that was given to us originally. This one is shifted its corner to 0. This is the result of subtracting the function v from u. And then if I shift my piecewise defined function so that its initial corner also is at 0, then this is what I get in my solution. I get both corners now at 0. But if I add w1, w2, and v, then I will unshift the things back to where they should be, and I can see that I get the solution that I expected to get. When we have more than one non-zero boundaries, then a similar process can easily give you a solution. If you have 3 boundaries non-zero, then you will have to have 3 subproblems. If you have 4 non-zero boundaries, you will have to have 4 subproblems. So it's not really that hard to extend this algorithm on the case of more general problems. It's just you have to be very careful at implementing things and make sure you don't skip any steps. So let me repeat the algorithm. First thing you do is you define the function v that brings your corners to 0 from the function u that has non-zero corners to the function w that has 0 corners. Naturally, this changes the boundary conditions for the function w. So w doesn't have the same boundary conditions as u. It has altered or adjusted boundary conditions so that every single boundary function converges to 0 at the corners. If you have more than 2 non-zero functions, then you will also have these boundaries filled in. Now each one of those boundary functions will create a subproblem. You solve each subproblem using the formulas that I gave you in lectures. Each one of those subproblems will give you just a component of the solution, so it's just going to be a part of the solution. And then the final step is you add all of the parts of the solution together, and you also add the function v, and that gives you the full solution. So this is how you solve a general boundary value problem with the Laplace equation. So that's it for today. I hope you liked the discussion, and I'll see you in our next video.